Now let's look at the binary op class on slide 28. And on the right-hand side, I've redisplayed slide 25, which shows the hierarchy of these classes. We're going to simplify the hierarchy slightly and just leave out expression and move up binary op to the same level as constant. Okay, so on slide 28, here we have binary op is a kind of term. Now, a binary op requires two terms to be combined together, either added or subtracted or divided or what have you. And what we're going to receive as arguments into the binary op constructor is a pointer to the left-hand term and a pointer to the right-hand term. And we're going to store those values into these left and right private data members, which are pointers to term. Now, we could have used member initializer list notation to initialize left to LF and right to RT, but our screen is a little cramped, so we've written it out vertically here. Then we also have a virtual destructor for binary op that deletes the left and right terms. Those are the only member functions that binary op provides, namely a constructor and a destructor. We've declared the destructor virtual, although technically we wouldn't have needed to do that since the term base class destructor is already virtual. Now, I want to point out here that binary op is still abstract because we did not provide any overrides for toString and toValue. Okay, so since we did not provide specific overrides for toString and toValue in binary op is still abstract, the same as term. Another thing that we've done here, since this is an abstract class to make our lives slightly easier, is we've gone ahead and declared the data protected. As a general thing, protected data is bad, but for an abstract class where you can't really use the class unless you inherit from it anyway, using protected data is okay. All right, next up we have plus, which is one of the possible binary operators that we might define. Okay, so plus is a kind of binary op. It is a concrete class, not an abstract class. It has a constructor that receives pointers to the left and right term on either side of the plus symbol, and plus simply passes those down to the binary op base class constructor using the member initializer list. Plus has a destructor that doesn't need to do anything. And here we have got toString and toValue defined. Now, what the toString function does is to compose a sequence of characters that is easy for a human being to read. That is, if we ask to see a representation as a string of this binary tree operator being used, then what we're going to see is an open parenthesis character followed by the string representation of the left-hand operand, followed by a plus symbol, and then a human-readable representation of the right-hand operand, and finally a closing parenthesis. So we would see something like open paren 3.3 plus 2.2 close paren if we ask to see a plus object displayed as a string. ToValue is similarly straightforward. The value of a binary plus on two double operands is simply the left-hand value plus the right-hand value. All right, so we would do the same kind of thing for minus, times, divide, and here finally, on slide 30, we have an application exercising these various data types. In fact, let me redisplay slide 25 again, because what slide 30 is doing is building this tree that's shown in these blue-green circles. All right, so the first thing we do is to create a new constant containing a value of 1.1, and the variable c1 is pointing to that new constant. Then we create a constant 2.2 that c2 is pointing to, and a constant 3.3 that c3 is pointing to. So at this point, if we look at our diagram, all we would have is 1.1 with C1 pointing at it, 2.2 with C2 pointing at it, and 3.3 with C3 pointing at it. But now we create a plus binary op. And plus has as its two children C1 and C2. So that is this binary op here, this plus symbol, and its left child is the constant that C1 is pointing to, that is 1.1, and its right child is the constant that C2 is pointing to, that is 2.2. Then in the fifth statement here, we're creating plus with the plus node, P1, as the left-hand side, and the constant, C3, as the right-hand side. So now we have created this topmost plus object. P2 is pointing at that topmost plus object. P2's left child is P1, and right child is C3. So we have now constructed this tree representing this expression. When we invoke toString on the object that P2 points to, well, recall what happens. toString is going to display a parenthesis and then the left-hand side with toString called on it, and then a plus symbol, and then the right-hand side. Now, the left-hand side here is a plus. So we're going to end up recursively calling toString again to handle this lower level plus P1. And so in that recursive call, what we'll get all right, my highlighter highlighted the leftmost parenthesis, which I didn't want. But that inner recursive toString is going to produce this string containing open paren 1.1 plus 2.2 close paren. That string is then going to become this left-hand side of the top level plus toString call. So that becomes the left-hand side with an open parenthesis in front of it, and then a plus and a 3.3 and a close paren. So there is our toString part. Here we're displaying an equal sign, which simply comes out as an equal sign, and then we're using the toValue function of the binary op that P2 is pointing to. And toValue, remember, is taking the left-hand toValue and adding it, this is literally an addition operation, to the value of the right-hand side. Now, in the initial call of toValue, the left-hand side is itself a plus. So we call toValue recursively to compute 1.1 plus 2.2, which gives me back a 3.3, and then we add that 3.3 to the right-hand side in the top level, and we get ourselves a 6.6 as our result. Okay, and that's it. So we now have a relatively straightforward expression evaluator, assuming that our expression only consists of constants and plus binary ops. We can add, minus, times, divide, and so forth.